Testing. Okay, audio works fine, I believe. Okay, so welcome to day 3 of learning art of problem solving pre-algebra. So I'm just gonna connect my iPad and get this up and running. Make sure this is on. Just wish this thing would work like immediately. Okay. What do I need to do? There it is. I don't know why that takes so long, but anyways. Let's go ahead and get the next lesson done. So we're still on chapter 1. We finished 1.3 multiplication yesterday, and the next lesson is all going to be about negation, I believe. Yeah, so 1.4 negation. So let's write that down. Okay, so take a look at it. So they're just showing an example of a number line. 0, -2, and 2. And to get from -2 to 2, we want to add 4. So yes, because -2 plus 2 is 0. And this is an interesting property. The opposite of a negation will always give you 0. So this always gives you 0. So that's neat. Okay, so definition, the negation of a number x written. So this is negation. Negation is when we say that we have a x or variable and we put a minus sign, but it's just a negation symbol. So this is the opposite of x. So if we want to get to 0, we do this. So we do -x plus x, which will always give us 0. So for all values x, the negation of x plus its additive inverse. Well, let's see if I'm using the terms right. Additive inverse of x. So if we take the additive inverse of x, add it, we always get 0. This could also be pronounced as -x. But I like saying negation x. I think it makes more sense. And then we can also say that the negation of x is x. We can say that the negation of x is negation x. Okay, so they're explaining why they're coming up with a new word, negation, when there's already negative numbers. And one of the examples they list is that, well, the negation of a negation looks something like this, which we know is x. Zero has a negation, which is just 0. Okay, let's move on to the problems. I think we get it so far. So So consider where the numbers at the ends of the facts above it on the line. After the first number, how is each number related to a number above it? They're all the opposite of each other. So 0 will be negative 0. Or negation 1 will be 1. Negation 2 will be 2. Well, we kind of answered it. Okay, next problem. Consider where numbers at the ends of the facts above are. After the first number, how is each number related to the number above it? Well, they're all just, so we have this. So that's 12, 9, 6, 3, 0. This is negative 3. And then, so this will be negative 3. It goes in the opposite direction now. So that's my answer for that. And then B, negative, or negation 1 times 3 will give me negative 3. Which, to be said, when we have negation x, this can be broken down into negation 1 times x. So that's an important property, I believe. And then we're already going to review. Okay, it's really hot in here. Okay, so let's review problem 16. Okay, B. So negation should be defined as the number we can add to get 0. Okay. So that explains why -0 and its negation will give us 0. So we can conclude that -0 or negation 0 is really just 0. Okay, and then C. Starting from 0, moving 1 unit to the right, we get to 1. So the double negation. So double negation 1, the negation of negative or negation 1 is 1. Again, we use a definition. We know that 1 and negation 1 sum to 0. Yeah, that makes sense. We know that's true. But we also know, oh, I guess, yeah, this can be broken down further. How did they write it? I'll write it like this. 0. So I guess we've proven, no, not really, but I'm gonna write this better. So we know that 1. Okay, I think I get what they're saying, because a positive 1 can be expanded to be the double negation. These are the same, or the equality between these two expressions are equal. And the reason why they said that, well, this equals 0, is because if the double negation of 1 is really just 1, then we know from the property they mentioned earlier that x, or negation x, is 0. Then we can safely conclude that, well, this is just the same thing, because x is really just the double negation, since that's just positive x. So we're just expanding numbers. So let's move on to D. Yep, that's what we have. They've just concluded the same thing, that the double negation of 2 is really just 2. Makes perfect sense. And problem 1.16, we saw the negation of -1 is 1. The negation of -2 is 2. Similarly, for any number x, the negation of negation x is the original number x. A double negation seems to cancel out, giving us the original number back again. Yeah. So we suspect that double negation equals x for all numbers x, and indeed in problem 1.16 we saw this pattern. But a pattern is not enough to be sure that double negation equals x for all numbers x. How do we know that the pattern continues forever? We can prove that double negation equals x for all numbers x using a very clever idea. Consider the sum. Okay, so they're actually writing a proof. Maybe it's probably a rudimentary proof since this is a pre-algebra text, but I was not expecting a whole proof to be written. And I kind of don't get what's going on. Like, here's the example they show. So I know that if we take x plus this portion of the expression, actually no, we don't need to do that. If we take this, group this first, and do double negation, then we know that this is just 0 plus double negation, and that gives us 0 plus x, so that equals x. Now let's see what they did. So that is, we're adding x, it's negation, and then it's double negation, or the negation of negation x. By the associative property of addition, we can then add these three in any order. If we start by adding the first two, we have 0, which is true because we've already stated this property. Yeah, and then we're left with this expression. However, suppose we start by adding negation x plus double negation. Oh, okay. So let's say that we did it the other way. So we did it the way we're gonna do it first. Well, we know that the double negation is really just x. So this just becomes 0. So we're left with x again. They word it differently. They're saying, however, suppose we start by adding negation x plus double negation first. Since double negation is a negation of negation x, holy crap, that's a lot of negations. But I think what they're trying to say is that negation x also has a additive inverse. So what do we get to equal 0? Like, what do we place right here? Well, we just add its additive inverse, which is that, and we will get 0. But this could also just be x. So to get 0. So that's our first proof. I think I get what they're saying, but I don't see how it proves it. Like, I see that it equaled x. We got the same result, but I don't see how we could just take x, the negation of x, and then the negation of negation x, and then say, oh, well, eventually it is equals x. That doesn't really make a lot of sense to me. We can prove. I'm just thinking here. What are we trying to prove? We're trying to prove that this is what we're trying to prove. Prove that double negation equals x. And we've done so by stating that if we take these terms, we get 0. But if we take these terms, we also get 0. I don't know, this is a very weird proof because I feel like we haven't proved something yet. Like we need to prove like this first. You know what I'm saying? Like I'm sure it's like a rudimentary proof, like very basic, but we haven't proved this first. So it's just a little weird. And then they ended with, we just showed that x plus negation x plus double negation equals both double negation and x, so we must have double negation equal x. I don't really get it. It's weird. Okay, here's what I'll do. I'll probably, when the stream ends, I'll try to figure it out. I'll go on Stack Exchange and see if anybody else has spoke about it. Because I get the properties they've used, but I don't know how they came up with, like, how did they know to do x, negation x, and double negation just from this proof? Like, what were they thinking? Okay, let's move on to the next problem. Consider multiplication facts below. The number at the ends of the facts and it'll start 12, 9, 6, 3, and 0. Yep, so we got that one right. We just noticed a pattern that is just subtraction of 3. That keeps on going down. B, so this pattern suggests that -1 times 3 gives us -3. So I think what they're trying to say is what we've written here, or where did it go? Well, I guess, I don't know. But basically this, that we can expand this expression right here to be this, or equal. But just as before, a pattern is not a proof. So let's prove that -1 times x is the negation of x. We can do this if we show that -1 times x plus x equals 0. What? So this is what they want us to prove that -1 times x is the negation of x, and this is what they came up with. Well, I'll try to solve it first, just with what I've learned, but I think it looks something like this. And then, let's see. I guess we could do this. And now we have a common factor. And then we know that this follows the property of that anything is negation, or the additive inverse results in 0, so that gives us back 0. And what did they come up with? Oh, cool. We kind of did it the same way. Kind of. They did it like this. They said that, well, this is just negative times x plus x, and then I could do this, positive 1x, and then we can use the x as the common factor. And now it's more short. I like their way of doing it. It's more succinct and simple. I like that proof. I understand that a little bit more, but I still don't. I want to know, like, why did they choose this expression in particular? So this is a question for later. I want to know why. Okay, so they've introduced more problems, so let's go on problem 18. So explain why negative or negation 2 times 3 equals this. Let's see. I don't know, it's pretty simple, right? That this is -1 times 2 and 3. This is all multiplication. So we could just group it differently. That's why. So just expand an associative property. Okay, from 19. Using the from explain why negation 2, negation 3 equals 2 times 3. This one's easy too. If we just use the following property, we have this, which means that we have a common factor now, so we can use a distributive property of multiplication over addition. Wait, no, we cannot do that. Sorry, yeah, I thought I saw a plus, but no, we would have to, so this is really just -1, or negation 1, negation 1, and then 2 times 3. Let's group that up, and then we can write it like this. Because if we assign this a variable, we can see a pattern. And we say, oh, that's really just A, which when we expand is 2 times 3. And that explains why we get that. So the answer is 6. And problem 20. Using the fact below, explain why negation of this expression equals, this one's easy. Okay, this is where we can use a distributive property. We just hand out the -1 because this is really, if we see this as just a variable, well, that's really just -1 times 4 plus 5, which we can then distribute the negative or negation 1. Which is -4 plus negation 5. I keep on saying negation or -4, negative, like, come on. It's negation 4. Okay, that's all the problems. Okay, now let's review it. So problem 18. We know that the negation is the same as multiplying by negation 1, so let's use that fact twice. Yeah, okay, so we did that. So we get that right. Okay. So when x or y positive, the equation negation x times y equals the negation of x times y. Says that new. Oh wait, if we go to the beginning of the book, they actually showed a problem where I was confused, but I think I finally get it now, because it's the same thing as this. When we take this out, we're left with this, which means that we can now group it like this. sorry. Like that. And then we're just left with 5 times 7. Okay, I get why a negative times a negative gives you a positive. Because you get a double negation. So problem 19. We kind of did it differently. They used the definition they learned from the previous problem to then solve it. So if I were to redo it, it would look more like this, where so they do this. And then we know that that's really just this. They're using the fact that negation x times y is equal to this, and vice versa. Okay. Make sure I understand this. I think I get it. Okay, let's move on. I think, okay, actually, let's take a step back and try to figure this out. I think what they're doing is that, well, -2 are they representing the y as this? Yeah, I think that's what they're doing. It's just a little weird to see because we see it as positive. So I don't know if that's true or not. Actually, I think we're wrong. I think it looks more like this. Remember, it's all multiplication, so this is really like that because we just multiplied it again. So now we get this. Okay, yeah, I get it now. So negation times negation gives us a positive answer. So -1 times -1 is 1. So we can say that negation x times negation y is xy. Okay, when x and y are positive, the equation says that a negative number times a positive number is positive. Students are often taught the chant negative times negative is positive. Now you know why the chant is true. I do know why. It's simply because double negation. If we take this and we take this, then we're left with this, which means it's a double negation, so that's really just xy. So negative times a negative is a positive. Okay, so how do we add negations? Let's find out in the next problem. So this is where we use distributive property. And looks like we get the same answer, so we just have to realize that the negation 1 is a common factor between these two expressions. So when we expand, or no, when we factor this expression, we're left with this, and now we can distribute the negation 1. And this is how we get the same answer. Okay, that was really fast once again. But we can do the exercises, and then that'll be the end of this stream. So let's get that done. So compute negation 631 plus 114 plus 631. I think we could just move those numbers around. Yeah, we could just move those numbers around. So let's take the positive 1. It's negation. And then 14, and we're left with this. Okay, that one was easy. What is the sum of all negative numbers that are greater than -4 or -5? Wait, 5, 6, 7, 8, 9, 10. Okay. Actually, let's do it the proper way. Let's try to reinforce that distributive property. Plus, it just makes more sense. One, 5, 6, 7, 8, 9, and 10. Boom. If we're left with -10, because now when we, I think it was this, we're left with this. Same thing. Okay, now we can move on to the next problem. I really want to show the steps to reinforce my understanding. So what is the sum of this expression? Wouldn't it just be 23? Because these are all the negations of it. So negation, negation, negation. We're just left with these two terms. So we'll say that 11 plus 12, 23. Okay, next problem. Negation 9. Let's see. How can I make this math simpler? I guess I could do this. Which gives me this. Yeah, this checks out. And then we have this. Booyah. Holy moly. This is a long expression. Okay. So I think I see the answer, but I want to make the steps clear. This is just positive. And then this is the negation of that. And then we can move those numbers around. Left with 0, because that's just a negation of it. So whatever, so just to explain it, 438 times 719 times negation, or -1, will give us a negative result. But this is the same number, but it's positive, so we get 0. So all we have to do is just subtract these, and the answer is 2. Okay, now let's check our work. See for right. Okay, 114, yep, get that one right. -10, right. 23, that's right. 105, that's right. And then the last one, 2, and that's right. Okay, we just did another section. So tomorrow we're gonna do subtraction, and then I think the last lesson of this chapter is division. No, it's reciprocals and then division. So after subtraction, we have 2 more lessons, and then we have to solve more problems. So looking forward to that. It's going to be a lot of fun. So yeah, see you tomorrow.